Actually, we are much fewer than before. I do not know if it is because of me or because of the good weather. Or is there any football match now? No, no football. So no reason to leave. Okay, okay, okay. Great. So we will continue with SysML and block structure in SysML, and I will start with some general introductions. So if you remember our platform-based system design approach, so this structural modeling covers the functional modeling part, the platform model, and also the architecture modeling part uh, in this platform-based system design. So we will learn the basic notations, basic building blocks of SysML, and we will mainly focus on the block structure. But just to give you some very basics in modeling. So as I formerly told you, a structural model is concerned with which elements of the system and how they are connected, related to each other. And also the properties of these elements are important. So there are many examples from information technology where it is very useful. So for example, data structured software components, network structure, and for example, software components running on hardware platform. So composite system can be defined in a way that it contains elements that are arranged in a specific way to attain a goal that the individual parts cannot satisfy on their own. So that's why we composing systems together. And during engineering, we can have various engineering processes, and we have various tools to design our system. And one is composition. When we are building a complex solution from an appropriate arrangement of simpler elements. And we can also use decomposition or factoring. That means that we are going to break up a complex problem or system into simpler parts. So these are the two main engineering processes. So using decomposition, we go from top to down, and it is an advantage that when designing a subsystem, its goal is already known. And the problem is that there are no working parts during development, and the problems can occur when the needs of subsystems revealed late. So we go from the system level to the subsystem or subsystem level. And when we build our system in a bottom-up way, using compositions, the advantage is that the subsystems can be tested one by one. And there are always some working parts during development, and especially management likes this because they can just see that something works. But the exact roles of the subsystems are revealed late. So usually what is advised is to use the meet in the middle approach and use these approaches in an iterative way. So usually at the functional model, when we are designing the functions of our system, we use top-down approaches. And we define the high-level components, high-level functions, and refine them until refine them to smaller units. And then we design the connections and the APIs. On the other hand, when we model the platforms, we usually use bottom-up approaches. We start the composition, we start the design with the hardware component library, and we compose these components into bigger components and model how they are connected. So what is your opinion? Why do we use this functional part, this bottom top-down approach, and in the platform model, this bottom-up approach? Yeah, that's true. So for software and for high-level functions, you usually at the beginning of a project you have some high-level goals that you have to reach. But when you want to model your platform, it is very rare that you develop everything by yourself. You usually have a collection of hardware and other elements that you have to rely on. So you have a library from which you can compose your system together to satisfy your needs, your requirements. So that is the main reason why we used to use different approaches. But actually, if you are a real hardware designer, then this can be changed. And just to show a small example of top-down structural modeling. So for example, we want to develop the graphical user interface of a calculator in a top-down design. So we start with the window, and we divide it to two parts, the menu and the main part. And then we further divide them into smaller parts and smaller functions such as editing, help, displaying, and so on and so on. So this is how a top-down design methodology can be, for example, applied. And in embedded systems, the decomposition or factoring means that breaking up a complex problem or system into smaller parts. And this is some kind of logical decomposition by functions and by the services we need. So for example, this is a very, very useful thing. This is a robot vacuum cleaner. I really like them because otherwise my home would be in a huge, huge mess. And the robot vacuum cleaner has three main functions. It has an exploration and navigation subsystem, a cleaner subsystem, and a monitoring subsystem. And we can further decompose these subsystems to reach the goals of the system. So, so this is how by decomposing we can reach our goals. But you can also use bottom-up approaches when you compose your complex solution from smaller parts. And for example, in software development, you can use it when you build your system from design patterns. You have this design pattern catalog, and you compose your components and your design patterns according to some assembly instructions, some design together, and then you will get the software system. So you can use them both. They have their advantages and disadvantages. As when you decide to use one, you have to take into account this information. Okay, so this was a general introduction, but now let's go into structural modeling. It is a very rich history in a variety of engineering domains, so mechanical, hydraulic, chemical, and software and hardware engineering, and also hybrid systems can be developed in this way. So in structural modeling, actually, we compose our system from building blocks. Or this can be done by hand or with some tools that helps us to compose our system. And when we compose our system, we use blocks. Blocks are reusable components, subsystems with some properties and connections. So here you can see many blocks actually. So this concept of block is the abstraction of all these things that you see here and that you can use in the engineering domain. Sorry. So I will use an example. I do not know if you are familiar with IKEA. That is a Swedish company, and you can just buy furnitures, and then you take home and you just build your furnitures at home. And I will just use this example to show you this how you can imagine and how you can build your system from blocks. So a structural model will guide the process of building this furniture from its building blocks. So when you buy this in IKEA, you will get the assembly instructions that actually look like this. You will also, and there are multiple levels of these instructions. So at the first part, then you build on top of what you finished here. And what you also need is a parts catalog that is provided when you just buy this furniture, this bunk bed. They provide you a part catalog that contains and lists all your components that you can use to build your system. And what you can observe is that what you define, what you have in the parts catalog, that you will use in the assembly instructions. So we have the definition here in the parts catalog, and they are used in these assembly instructions. And you have to observe that the same part definition can be used multiple times. So here we have this, I don't really know what it is, but you can use it here and here. So it can be used in various places. And here we have some properties of this block. Actually, for example, the patent number and many other information. And when we use this element here and here, they will get some more information. They will have some more characteristics, namely, for example, the orientation, how we used them. And then finally, at runtime, when we have our bed and we are just sleeping in it, actually, there will be also another, and we will also know some more information about these specific elements. For example, the stress that they have. So we have the parts catalog, we have the assembly instructions, and we want to reach the real system. So, and we use actually the same elements that are defined in the parts catalog. We use it in the assembly instructions, and then we reach the real system. So in the parts catalog, we defined the blocks and their types. Then we showed how one should use them. This is a kind of template of the usage. And here is the block instance of our small element. And it is a real physical object in this case. And what you can observe is that here at the assembly instructions, this is not an instance of these types because, as you could see, we could just instantiate it multiple times in different ways, these things. And the assembly instructions and the block usages actually do not define the type of the block instances here. So here, at the assembly instructions, we defined the role of the blocks in some composition. And this is how you can build a system with the help of all these blocks and elements. And when so, for example, here, as you can see, we defined the type. For example, it will have an attribute of an integer. And here we further refine it that it will be a private integer. And here we will get in the real system that it is 42. So this is how you can reach your final system through steps of refinement. And as you could see, and as I mentioned, some parts maybe themselves also be composites. So at first we construct this, let's say, the frame of our bed, and then we add these additional things to it. And here we used those things that we finished here and we defined there. So we can hierarchically compose together these assembly instructions and systems, and we can go on, because from the bed frame we construct the bed that we will place in a room and then finally in an apartment. And SysML wants to support this kind of modeling. As you remember, UML uses a software engineering terminology. In UML, blocks can be regarded as classes or components. The parts catalog is the class diagram or component diagram, and the assembly instructions actually are the composite structure diagrams. SysML is a more general engineering, uses a more general engineering terminology. So we are very lucky because in SysML, blocks are called blocks. That's very easy. And they merge the UML class and component features. And there are many extensions such as flowports, physical dimensions, and so on. And the parts catalog is called block definition diagram, BDD for short. And the assembly instructions are called internal block diagram, or IBD. You can imagine them. So I mentioned you, BDD is our part catalog. It is used to define the composition and the decomposition. So they are related to UML class diagram and UML component diagram, but they are not the same. So be careful. And BDD provides types for the IBD. IBD provides the assembly instructions for our system, and it defines the connection and the communication. It is more related to UML composite structure diagram and UML object diagram, but they are not the same. And what is important, that all these language elements are constructed to support the design methodology of top-down and also the bottom-up construction of systems, because SysML provides only a language, and you have to decide where and which approach to use. So if you use blocks for, if you want to define the functional architecture, then blocks can represent functional units, components such as software modules, microservices, devices, and so on. And what is important, that part-whole relationships that are represented with the help of blocks, it doesn't necessarily mean a physical containment. And connecting blocks doesn't necessarily mean physical linkage. So it can be dependencies or some kind of information flows. So now we have some impression about SysML and structural modeling in SysML, but we should go into the details related to block definition diagrams. So as I mentioned you, it's a diagram type in SysML that is related to some other UML model. So blocks are represented, are noted quite similarly to classes. So blocks are the fundamental modular units for describing our systems, and compartments are used to depict the parts, properties, references, and many, many other things. And the block can be nearly everything, starting from system, subsystem, hardware, software data, and so on. And a block is a UML class with the block stereotype, but actually the modeling tools the modeling tools do not use this notation actually. So, but you have to be aware of that. So a block has a name and it has parts. This is the parts compartment. So here you can see the contained blocks, and also it can have references to other blocks. It can have values like UML attributes. You can define constraints to our blocks, ports, and you can also hide these blocks on the diagram. And blocks can have associations to each other, and an association or reference is a relationship type between two blocks. It can be undirected. That means that the reference property in both blocks, or directed. That means it is a reference only in one block to the other. So this is quite similar to UML. This is how you navigate through the associations. And similarly to UML, we can use end properties such as role name, multiplicity, and constraints, as you can see here. And you can also use association blocks. That is an extension when you actually, to an association, you define a block that will contain the properties of that association. So this way you can express more complex associations. This is actually quite similar to some concepts in database theory. So who has done database development, this concept can be that concept is quite close to that. And we can have composition when the container component owns the contained components, and it aggregates all features of the contained components. And you can also use generalization similarly to UML, to what we learned in our last lesson. So generalization means that the components share common features besides other properties, and component can be used interchangeably with their descendant components. And you can also use composite associations, part associations, that specifies a strong whole part hierarchy. So at the whole end, you have the black diamond. At the part end, you have the role name as it is depicted here. So our smart transportation system is composed of a transportation system and the zone controller subsystem. And here you can define the multiplicities. similarly to UML. So the generalization has a the generalization comes from the object-oriented programming, and it works very similarly to UML. So the key idea is the substitutability and the main usages, and we want to classify components. For example, when we want to move from specific to a general, and in the other direction, if you want to have more specific configurations, more specific names and values, in this case, we move from the general to the specific. And with the help of generalization, you can add, define, and redefine properties. And they can be used not just for blocks, but as you could see formerly, it works with many other things. And in SysML, multiple inheritance is allowed. And also the concept of generalization sets appear in SysML with the same concepts such as complete, incomplete, overlapping, or disjoint. And the big advantage of SysML is that it provides a traceability. And as I formerly mentioned, blocks can realize requirements, and it can be represented by this satisfy relation between subsystems and requirements. And you can also use the special type of association called allocation to platform elements. So when you develop your platform model and you have also your functions, SysML supports you to allocate your functions to your computing units. So let's continue with the internal block diagram that is also in SysML, and it has the corresponding parts in UML. And it defines how you can break down a composite block into parts and how they are composed together to constitute the large block that contains them. So the objectives of this internal block diagram is to describe a composite block as connected parts. And we use the contained and reference blocks defined in the block definition diagram. And we use associations and interaction points, namely ports, to define some relation between these blocks. And we also specify connectors, such as data flow between the ports or between the parts. And you can use item flows and various other kind of language elements. And as I formerly mentioned, in the internal block diagram, we define mainly a template. It is called instance specification. And the semantics can be illustrated. So if you instantiate the composite block, then you will also have the following parts arranged in a specific way. So that is what in an IBD you define. So as I mentioned you, IBDs are used to represent a block. So here you can see that there is a block, a transportation block that contains a safety module, and it has a reference and association to a zone safety module. And with the help of the IBD, we will provide a template for the implementation of this BDD. So you just have this IBD, and it contains the safety module, and it references, it has an association to the zone safety module. And you use here actually the elements defined here. And the default multiplicity is 1. And you can also instantiate and use the connectors. And here you can see that there was the zone safety module association, which is used here as a connector. And when it will be used in a physical system, then we call it, the actual instance is a link. So here you can see the association connector, that is the template for the links. And you can nest the blocks into each other. So you can use additional IBDs to define the hierarchy, and it is commonly used. But you can also use encapsulation. So because here you can see that the connectors can cross block boundary. But if you mark a block encapsulated, you can forbid this kind of usage. And as you remember, this can be very, very helpful, because this can prevent other elements and other engineers to look inside our blocks, our implementation. And this is mainly about the separation of concerns I emphasized you yesterday. And the fully qualified name comes from this containment hierarchy. So as you go down in the containment hierarchy, you can just get the fully qualified name. And how you define interaction between blocks, and how you can define relations and other kind of communication in IBD. We will use ports and interfaces for that purpose in our internal block diagram. So what is a port? It is an interaction point with external entities, limiting and differentiating the possible connection types. So here you can see a port. This can be also a port. Or here you can see an example of a REST API that is also a port. But if you want to model, let's say, Natal can also have a port, and it can be the real port of the city. So here is where the external entities can connect to each to us. And how and when to use ports? Actually, if you use the bottom-up method for system design, the problem is that you start by defining the interfaces, and then you want to, as you go on the development process, to realize that these interfaces, where and when to use them. And ports provide the abstraction at the IBD level, and they provide the interfaces. So you can attach the interfaces you defined formally and use them in the internal block diagram. And you can use, you can just add multiple ports, and you can use the same interfaces on them. So somehow interfaces will define types for the ports. In a top-down method, when you have defined a connection, but it is not detailed enough, and when you want to refine it, you can use ports to refine this connection and refine it to represent our refined system design. I mentioned you the problems encapsulation. So the problem is that the connections can cross the block's boundary, and it is not good from the maintainability point of view, and you want to avoid that. And you can just use ports to hide the internal structure of our blocks. So this way you introduce the blocks and hide the internal structure of our block. And you can also use ports to show that an interaction point has a special role. So for example, you want to represent a physical connection point. And in this case, ports can be typed by a block with its own properties and behaviors. And you can add more information to these ports with the help of additional blocks. Standard ports are used as an interfaces for communication. There are two types. The provided interface, and that is this ball that defines a service that this block will provide. And the required interface, we can use the required interfaces in ports, and is represented by this socket, and it represents that we want to use a service. And the ports can have multiple of required ports, and you can combine them together this way. And flow ports are those where the connection is described by flowing items. It can be continuous, periodical, aperiodical, and it can be nearly anything. As I mentioned, SysML is a general language. So you can just say that data or material or energy flows through these ports. And these flow items can be typed by blocks, value types, signals, or whatever you want. And there are mainly two types of ports. One is the full ports that can have internal structure, and you can also define behavior. And you can also use proxy ports that do not own any features. They only expose the internal features of the blocks. And you can use composition instead of the full port. For example, here you have a full port of a smoke sensor, but you can just replace it with a proxy port, and then you can implement the what you wanted to implement in this full port inside your IBD. And you can also nest the ports. So full ports can have other ports, and they can be composed together to provide some, how to say, very complex functional, very complex port structure. So these were the main building blocks of SysML block diagrams. And now I will show you some other elements that are very useful in SysML, and you have to be aware of them. So SysML supports the modeling of logical and physical data. So you can define value types. And the value type is used to provide a uniform definition of a quantity with units that can be shared by many value properties. So we have the primitives such as Boolean string complex, and you can have units and quantity kinds. They were formally dimensioned. And for example, a quantity kind can be a length, energy, time, and the unit that you use to define these quantities, for example, meter, inch, watt, secondum, etc. So it has a quantity kind, and this way you can define physical parameters. You can define and do type checking in your system. And these value types work in the way that the equality means that you compare the values. So similarly to the basic data types, these value types behave similarly. In this way, you can add data, various data to the blocks, and actually, as I mentioned you, that the value of the attributes of the block is defined in the BDD. It is used in the IBD, and then at the runtime, this value may change over the time. So that is how you can imagine. So for example, if you have a motorcycle, then in the BDD, you will say that motorcycle has 2 wheels. In the IBD, we will say that this motorcycle has a wheel of size something. And then when you have your motorcycle and you just drive through the city, then it will have some speed, for example, and other attributes. So these are the different levels of abstraction during the development. And you can also use signals in SysML. And the signal defines a message that can be sent and received by a block. It has also attributes such as it was the case in UML, in class diagrams, and it can be used by the interfaces. So for example, here you can see the signal of the train current speed with the current speed and direction attributes. It is also important sometimes to define well-formness constraints. They describe additional constraints that should be satisfied by every instance of your system. They can be structural constraints. For example, a turnout sensor should be connected to exactly one zone controller. There can be value constraints. For example, the operator should be at least 175 centimeter tall, or the components should have a unique name. And we can also provide behavioral constraints that the CPU should receive certain amount of electricity. And these well-formness constraints are used for the early validation of your system. So actually, the meta models and these block definitions actually can let you build even wrong systems that are not the ones that you want to have. And in this case, you provide this additional constraint, this additional well-formness constraint. And here is an example from the AutoSAR domain. AutoSAR is actually a huge language family used by the automotive industry. And they have huge models, and you have to, the earlier you find the error, the easier and cheaper to correct it. So you want to find these errors as early as possible. And you can just define patterns, well-formness patterns that you will try to find the violations of these patterns in the models. And there are many difficulties beside the complexity of the model and their size. So you need some language support to define these patterns and so on. And this system signal group design rule is from AutoSAR that I show you in the last slide. And the problem is that actually in AutoSAR, they have huge models. So sometimes more than 1 million elements, and the models constantly evolve. And there are many design rules that you have to check. So you need some language and you need efficient algorithms to find these design rule violations. This in SysML you can also use constraints. Here you can see an example. You just use the constraint compartment here. You can use, for example, plain English, or you can choose a formal language such as OCL. I mentioned you in the introductory talk. And if you use a formal language, such as we did also in the AutoSAR model, then you can do automatic validation. And these constraints also can be defined in SysML by using a separate block. And what is important here, the constraints refer to your designed system. And I mentioned you that in SysML, you can have also parametrics diagram that mainly focuses on the environmental constraints, the constraints represented by the nature. So if you use a formal language to describe your constraints, such as the OCL, the object constraint language, then you can get this early validation of your models. Here you can see a simple example of an OCL constraint that will enforce that the names of the components are unique. So it tells us that for the component, for all instances of the components, for all C1 and C2, if they are different, that implies that their names are also different. So OCL can be used for this purpose, but there are also other techniques. For example, the Viatra language, that is an open source Eclipse project, and it has a very expressive query language, and it uses graph pattern matching algorithms to find design violations. And for example, if you want to express the same constraint like before, then you will define this pattern, this name collision pattern, that tells that the components must have unique names. So by using these algorithms, you can define rules and you can find design violations at a very early stage of the development. I also want to tell some words about profiles because they are used for extending UML and SysML. And for example, a SysML is defined as a profile on a subset of UML. SysMod, the methodology for SysML, also defines a profile for SysML. Parte is also a profile that is used in the modeling of real-time and embedded applications. And tools usually support the creation of these profiles. So here you can see an example profile where we define stereotypes with attributes and relations, and these stereotypes extend a meta class. And then when we use instances of this meta class, then we can use those attributes that were defined in the stereotype. So now we went through the basic things related, the basic elements and semantics and syntax of SysML. And now what I want to show you is a basic introduction to state-based modeling, because tomorrow we will continue with behavioral modeling, And tomorrow we will also have laboratories. So I think we need all these definitions before the lectures tomorrow. Do you have any background with formal methods, formal languages? Does anybody have any background? No? And another question, have you ever used regular expressions? So, for example, in Linux, you can use them. Okay, so I will go into these things now. So, as you could see, we can define structural static aspects of systems, but sometimes we need to define the behavior of the system. And this will define, for example, for this robot vacuum cleaner, that what it will do if we send some comments for them. And to be able to do that, we will define the basic concepts of behavioral modeling. So there are multiple viewpoints of behavioral modeling. So if you are interested in what the system does, then we are interested in event-based models and process-based models. And if you are interested in what are the properties of the system now and how do they change, then you definitely need state-based models. And now we will learn the basics of state-based models, and then tomorrow we will extend it with many other concepts from the other type. So in order to be able to define state-based models, at first we have to define the concept of event. An event is an instantaneous change, for example, at the input-output of the system. And an event stream is a stream of events and that comes from an input or goes out on an output. Event space defines the allowed events. So, for example, the readable input values or the emittable output values. And we have a series of instantaneous events. That means that at a certain time point, we will have at most one event. So these things that are related to the definition of event. So for example, if you want to define the event stream of your smartphone, where the event space is that you can get an email, an SMS, or a battery low message, then your event stream is composed of these kind of events. So here you got an email, then an SMS, email, and so on. And here you just lose all your charge from your battery. So these are the basics for defining events. And in state-based systems, we have to define the concept of state space. The state space is the set of distinct system states from which always exactly one element, that is called the current state, is characteristic for the system at the time. So at the time point, one element of the state space will describe our system. So just to show you some example, the days of the week: Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday, it's a state space. Or I will use the states microwave oven example. So for example, the states of the microwave oven, that full power, defrost, or off. This is the state space of the microwave oven. And an example for the current state is that today is Thursday. Well, that's not true, but that is just an example. Or the microwave oven is off. So always exactly one element is characteristic for the system. And so this means that not any set of states can be a state space. So you have to, we have to define the concept of completeness. That means that always at least one of the states is active. For to show you a counterexample that is not a state space in this sense, is that, for example, if we say Monday, Tuesday, Thursday, Saturday, because this is not complete. So sometimes we are not in any of these states. Actually, oh no, we are not Tuesday, so it's not a problem. But actually, there are some days where you are just not in any of them. And another important property of state spaces is the concept of mutual exclusivity. That means that only a single state can be current in the moment. So for example, a counterexample is the working day, weekend, afternoon, because now it's working day and it's also afternoon. Well, now an evening, but let's say. And for a microwave oven, for example, the door is open and the microwave oven is switched off. This is not a state space because they can be both true together. And we have to define the state refinement and state abstraction properties. So state refinement and state abstraction respectively are set refinement and set abstraction on the state space that result in a new state space. So you can imagine them as you have this abstract state space and you will refine them to more states. So for example, from A2 you will get just one state, B1, but from A1 you will get a set of states called B2, and from A3 you will get as the set of states B3. Just to show you an example for the refinement and abstraction. So here you can see the weeks of the day. And we can use abstraction if we say that, okay, we are not interested in exactly which day it is now, but we are just only we are students just interested in if it's a working day, because then we have to go here. Or if it's a weekend, because then we can drink cachaça. So I heard that it is very, very typical that here students drink a lot of cachaça. And I was told that because I drank at the weekend cachaça, and I was told that that is not for me, it's for students. But I liked it. So, but this is a very important abstraction because it just grabs the essence of being a student. We could call cachaça days or not cachaça days. That is also an abstraction. So, and in the other direction, we get the refinement. So we provide more informations because there are some good classes during the day, during the week. So we have to know that if it is Tuesday and I will present to you, or it is Thursday when Professor Andrea Bondavalli will give you an amazing, a very, very interesting lecture. And you will like that so much. So it's important sometimes to know the details of the working days. So this way we can define refinement, and when we want to have less information, then we use abstraction. So, and just to show you another example, for example, the microwave oven, where we have the concrete, the refined is composed, refined state space composed of full power, defrost, and off. But actually, we are not interested in the full power, the difference between full power and defrost, because, you know, both are just radiating, and it's very dangerous. I do not know if you have seen, there were some American people, they wanted to dry their cat in the microwave oven. Actually, it's not a good idea. It was very, very bad for the cat. And that is, we are just interested in that, if it is dangerous for us or not for us, but for cats, because I think that nobody has already tried to put themselves into a microwave oven because it might be too small, but if it is dangerous for cats or not. So then we will just have one on state instead of having the full power and defrost state, but we will not refine the off state and we will not abstract it because that contains enough information and the proper information at both levels. So by using state refinement, we can add implementation details during the design process. We can use specialization and we can extend the behaviors. And we can also define the joint behavior of several subsystems. And then by using refinement, we will have more information, more knowledge. So that's some kind of trade-off. And when to use state abstraction, if we want to express somehow the uniformity of some states, and then we use abstraction and merge substates with similar behavior. And it is also useful if you want to hide details that are irrelevant. And sometimes it is easier to work with a smaller, with a easier, simpler state space. And it can also yield less storage or less storage requirement for the states. And it is easier to process. And you can hide details. So abstraction helps you in designing these state-based systems and to provide the appropriate information at the individual levels of the development. And you can relate it to many other engineering domains. So many engineering domains have potentially infinite state spaces. For example, the state, if you just consider the state variables of airplanes or nanosatellites or rockets that you develop here, it has an infinite number of states. So we have the speed, the flight altitude, and the rise angle. And from this, you can reach actually concrete and finite number of states by using quantization, if you discretize your states. But for typical IT system, they have discrete states and no continuous change, and they often have finite state spaces, and they have instantaneous state transitions and fixed states between. So in this case, to use state-based models is very, very useful. And you can combine them in a hybrid way. So if you have some continuous variable, for example, and some discrete variable, you can combine them. For example, in the bath tube, there you have the discrete variables if the top is open or closed and the plug is in or out. And there is also a continuous variable that is the water level that spans between 0 and 60 centimeter. That is the top of the bath. So the values of the discrete variables influence the values of the continuous variables. And you can use abstraction to catch, to grab the most important part of the behavior of the continuous part. So by using predicate abstraction, you can just abstract the the values of the continuous variables with the help of some predicates. Let's see an example. So for example, a predicate can be for the water level in the bath tube. For example, that the height of the water can be 0 or bigger than 0. Or we can say that 40 centimeters, actually it is the maximum level. So we can express if it is below, the water height is below the maximum or above. And the top of the bath tube, the rim, is at 60 centimeters. So we can say that it is below 60 centimeters or it is 60 centimeters. Actually, in a fortunate situation, it will not grow above that. So that is the limit. So we have these predicates, and we can use these predicates to tell that if the bath tube is empty, it means that the depth of the water is 0, the height of the water is 0. We can say that it has a normal level if it is between 0 and 40 centimeters, because if you just go into the bath tube, sometimes just fell asleep, and it is very dangerous if the water level is too high. There is a critical level which is above 40 centimeters and below 60. And we can use the predicate h equals 60 to indicate that the tube overflowed. So this way we can use predicates to express those parts of the continuous state space that are relevant for us, for example, from the control point of view. And this is called predicate abstraction, and these are called the predicates in our system. Another important thing in state-based modeling is that we can partition our system from multiple waypoints. So there can be multiple correct state spaces of a single system. For example, two disjoint state spaces of the microwave can be according to the power, that full power, defrost, or off. Or according to door position, it can be open or closed. They are actually not completely independent, because if the door is open, the power must be switched off according to the cat experience. So in this case, the state space of the so it is decidable without knowledge of the system state, which state of the subsystem is the current state. And if we consider the two state spaces together, so that was the power and the door, then we can combine them together. So we can create a table from that. This is for the power and this is for the doors. And we can combine them together, and we can say that the system can be in a full power and open, defrost and open, off and open, off and closed, defrost and closed, full power and closed state. So this is actually the product of the two state spaces. And in this direction, you still get an abstraction of the composite state space. And the remark is that in this case, if you just compose the direct product of the two state spaces, then you will reach that the size of the composite state space is is just S1 times the S2, so the subsystem state spaces composed together. So this was the direct product of state spaces. You use the composition operation over the component state spaces, and that will result in a new state space that is called the product state space. And it is formed as the Descartes product of the sets of the component state spaces. And in the product state space corresponds to each combination of the states of the component state spaces a combined state. So it is kind of vector representation. So just to see an example, here we have a clock where we can have AM, PM from 1 to 12 hours and the minutes. And from this we can construct actually the full state space of a day. All these are sub-state space of a day, and we can just construct the full state space together. And you can use projections. So that is an abstraction operation, as I showed you before, that will just keep one or more component and neglects the other. So for example, for this clock, we can just say that, okay, we are just interested in if it is PM or AM, and how many hours do we have. So we can just project and cut this part of this clock. So this is how projection works. And when we compose system together, subsystems together, actually sometimes they are dependent on each other. So these state variables depend on each other. So not all combinations can actually appear. And this means that the composite state space can be more fine than the product. So for example, as I mentioned it cannot happen that the microwave oven is going on full power and the door is open, because it is very, very dangerous. So we eliminated these two states that are dangerous, because here we know that the door is open, so we cannot be in full power and defrost mode. But what is important, this is still, this projection, it is still a state abstraction here. So even if we removed some state from the composite state space, this is still an abstraction operation. And as I told you, the composite state space is more fine than the product because we excluded two composite states. And this way, the refined state space has fewer states. And until now, the state space refinement resulted in a higher number of states. But an important thing is that it can also reduce the number of states. And this way, the system is more restrictive. It has less behavior than the composite state space without this restriction. And you can also use decomposition of the state variables. That is the reverse order. So we have these states, and we can just decompose them to two state variables. One is for the power, and the other is for the door. And this is a kind of abstraction, but it can be very, very useful because, for example, we can process state variables separately, or to store state variables separately. So sometimes it is very, very useful. Okay, so we defined the basic operations on state-based systems. I see that you are very tired. I will try to be fast. Maybe if you don't want, I will not show you the case study today. We will decide. So we have to also discuss automata and simple mealy automata. So we have the state space of the days of the week, and we have the function of the state, the current state, that is a function of time. So at each time point, it will just get this state variable will just get its value from one of the state space. So here is the uh, actually here is the working of a week. So from day to day we change the state, and actually each state transition, each change of the state is regarded as instantaneous. So it's a discrete event that will happen immediately in time at the end of the day. So, and here this this window, the size of this window is fixed. It is 24 hours actually. And state transitions can be represented by relations. Relations from the mathematical sense. So we have the state space S, and we have the event state, event space that are the state transitions that are represented, and the state transition rules are the following as represented by relations. So R1 is when we move from Monday to Tuesday. R2 is when we move from Tuesday to Wednesday, and so on. And this way we can define that from Thursday, for example, the system can move to Friday. And if we represent it as a graph, that is a common canonical representation. So we see these relations, that the state transitions that change the state of our system. And it is also called the state graph. And it's good to know this kind of representation, because you can see many papers and definitions that rely on this kind of definition of state transitions by representing them as mathematical relations. So there are multiple possibilities regarding state graph. It is possible that the graph is complete, all transitions are allowed. For example, for a small kid, if you have these states that sleeping, playing, drinking, actually can change from all the states to all other states. That can happen that not every state is reachable from each state. For example, if we just consider the state graph of a glass, empty, full, and broken, actually from the broken, it is very rare that we can go back. So it cannot be empty or full anymore. And that can also happen that some states have multiple successors. For example, in our favorite microwave oven example, from the off and closed state, we can go to the off and open, or we can start defrosting in a closed state. So there can be, this way we can represent some kind of non-determinism. This kind of non-determinism comes from either from the behavior of the model system or from the abstraction introduced during modeling. And actually, this means that, for example, if we ignore some internal variables, some inputs from the environment, then it is very easy to get a non-deterministic model. And by using this formalism, we can build the simple Mealy automaton. So here you can see example of an ATM system, where this is the state space of our system, and we change our state according some events that happens. So what you can see is that we have labels in the transitions, and actually these are events of our system. They are instantaneous events, and a transition can be associated with an event. And possible interpretations, the event can be the result of the transition. This way you can define some kind of post condition. So at the end of the defrost, the microwave oven just ring a bell, and then it will be switched off. Or we can cause or trigger the transition. For example, from the switched off state, we can start the defrost by pressing a button. And a transition can have multiple layers. For example, reading input and writing output. So for example, if the input is a timer signal, that will trigger the transition, and it will just react with ringing bell. And here you can see a more complex example that where all transitions are deterministic, reading input and they are writing an output. But if we change this rule to go to S0 back, then we will see that for both inputs, we will go from S2 to S1 and provide some output. So to be able to model this kind of systems, we need some extensions. So in classical system theory, we have the system, we have some inputs, transitions, and outputs. That the outputs are the function of the input and the state of the system. And during this, during receiving inputs and producing outputs, we change the state of the system. So what we need is some extensions of Mealy machine. So we can actually model non-deterministic behavior. For example, we can have spontaneous transitions without reading input. That means that it is an internal transition and an effect of a non-modeled event. For example, when the heating finished, the oven switches off. And if we do not model the timer, then it will be a spontaneous transition. We cannot tell when it happens. We can have multiple output channels, actually separate event streams with disjoint signal sets. And the rules will emit signals to a specific subset of channels. And we can also have multiple input channels. And the transition rule reads input signals from a subset of channels. And this can also cause non-determinism. So just to see a simple example, how you can imagine it. Here is this extended state machine. It has a name. Here you can see an input channel with a signal set with an event space, and the output channels with the signals and token symbols. And here you can see a kind of non-determinism, because from I1 here both we read 0, and we can go to S1 or S2. Here you can see that these two transitions differ only in labels. And here you can see a trap, a sync state. So from here you cannot go to anywhere. We can use loops, self loops, and you can model internal transitions. That is some hidden part of the model that you do not model. And you can also have some kind of potential conflict, because you have to decide to which direction you should go. So what to do with unspecified inputs? So we need actually rules for that. If there is no rule, then for an unspecified input, then actually the transition is not allowed. Or we can just consider that there is an invisible loop transition. So all unspecified input tokens are consumed but ignored. So we do not do anything without them. Or we can consider these models invalid. And it is very often the situation in critical embedded systems where you must define every kind of behavior for every kind of events. So let's see a small example of communication protocol, and I will also show it to you in a modeling tool. So we want to model communication protocol that can receive packets that can be lost or can be damaged, and we will provide acknowledgement and or resend messages. So our input is composed of valid or damaged messages that comes from the sender, and we can provide the sender acknowledgement or an neck message, and to the application we can just show that the packet arrived. And I will show you this system in a modeling tool. So tomorrow there will be a laboratory, and I want to show you. We are going to use just a moment. We are going to use the Yakindu state chart tools, and so this will be the tool that we are going to use tomorrow. You can define your state chart models with the help of it, and actually we will do the assignment in it. So it is able to you are able to define state charts in this model where you can define interfaces. So if you remember, I do not know if you see it from the last rows. Oh, so you should come closer. So this state machine can have interfaces. For example, the input interface. If you remember, we can have valid packet or damaged packets. So in our interface input, we have two event types. One is valid packet and the other is damaged packet. So we just say that it is an input event valid packet. And we can provide feedback to the sender, these acknowledge and not acknowledged messages. They are sent through the sender interface, and they will be the output events of our system. And as I mentioned we have also an interface to the application where we can depict that the packet arrived. So here is our small example, and you can use these events in your system. So for example, we received here an input damaged packet, and then we raise this neck message to the sender. Or if we received a valid packet, we go to the arrived state and we raise an acknowledgement to the sender, and we raise a packet arrived message to the application. And when this message arrived, actually we just do not anything to damaged messages. So there is a self loop here, and this tool is very nice to use. So you can just use the content assist that will help you, and if in the input for example, we can choose that a damage packet, then we don't do anything. And if we get a valid packet, then we will raise acknowledgement message to the sender. And you can use even composite states and many other things that we will learn tomorrow. And you can actually simulate this system. So just a moment, it will start, hopefully. I do not know what happened. Okay. Maybe I modify. Oh, I have to save it. Sorry. I have to close all the other. So as I. So we are at the beginning in the waiting state, and if we send a damage packet, then we will just stay here, and we will just stay there as long as there is a valid package. And then we can send the valid package, and we go to the arrived state, where we can still have different packages. For example, by sending a valid package, we will raise a sender acknowledgement, or we will just if we get an input damage packet, we will do nothing. So it can also be used for simulation purposes. And tomorrow we will learn the complex states and how we can use abstraction in the design of these kind of systems. And we will learn how to use this tool, and you can do your exercise with the help of these Yakindu state chart tools. This tool is open source, so you can use it. You can download it. Tomorrow I will prepare it for your computers in the laboratory. There will be an image, so you can just even take it home, and you will have the exercises. And this is actually the end of my state chart presentation. My question is that do you feel enough energy to have a short because I wanted to show you a short case study of architecture modeling. Do you think that you will be able to pay attention, or do you want to go home? Who is interested in industrial case study? Okay, that's enough for me. Thank you. I will be very fast. So just a moment. So I just want to show you this case study because it was a real industrial project where we combined structural modeling and various techniques and technologies I have already mentioned to you. So the goal of this case study was to analyze the non-functional requirements of systems. So in this case, we have the systems engineering model and the reliability and dependability requirements. And from this, we have to create a stochastic model from the systems engineering model and the stochastic metrics according to our requirements. And actually, this is very, very cumbersome to develop these stochastic models. So I've done it by myself, and I don't wish to anybody of you to do it because it's very tedious. And then we run the Markovian stochastic analysis on the stochastic model with the stochastic matrix. Actually, we used numerical solution algorithms here. And then we will get the values of metrics. In our case study, it was a redundant sensor architecture and a software that just made sensor fusion. And this case study is from the automotive domain. And in this case study, there were multiple actuators connected to the microcontrollers, and each microcontroller needs precise up-to-date sensor data. And there were a failure detection and avoidance mechanism with using self-checking mechanisms, local sensor redundancy, and cross-checking with remote sensor data. So I do not know how familiar are you with avionics, but there was some plane accidents related to Boeing. Have you heard about that in Ethiopian Airlines and in Indonesia? Because the designers of the sensor network in the new generation of Boeing, actually, they wanted, actually we developed a very similar system for the automotive domain. But in that case, the problem was that they didn't use this kind of techniques to estimate the reliability of their system. So that's why so many people died. But well, actually, in the automotive domain, you cannot do that because the standards are very high. So here is sensor architecture. The microcontroller runs the sensor fusion algorithms. We have the sensors with self-diagnostic, and the microcontrollers compare the inputs for increased fault coverage. And the microcontrollers also are also connected to each other, and they run these fusion programs to find the problems. And a sensor failure is detected by a self-check mechanism. In this case, the fusion program falls back to the other sensor data. But sometimes the self-check cannot find the error. And in this case, invalid data will be transmitted to the microcontroller. And in this case, we will run a comparison with remote reference to reveal the problems. But the problem is that the remote reference is not sufficient for controlling the actuator. So this is a very real-time system. And even actually, all these microcontrollers and sensors are in a very small box. And this, even this small distance is too much to provide the real-time control. And when all local sensors are lost, the system shuts down. And we had the architecture model that you could see here, but we also had the fusion program with the help of that tool that I formerly mentioned you. So we used Yakindu to develop the sensor fusion program. Here you can see the interfaces, the guards reading self-diagnostic and other value comparisons, and we have the control locations and the degraded states. And then when there is a big problem, we have to terminate the process. And we identified system level hazards. The degraded operation was that if there was a sensor failure, then the system operated for only a limited amount of time, and then it shuts down. And an emergency shutdown is initiated when further failures occur in the degraded state. And what is very important is the sudden loss of actuation. Actually, this is what happened to the Boeing, and that's why so many people died. And the sudden loss of actuation is when a microcontroller relies on invalid sensor data due to a sensor failure. And in this case, the system is unsafe. And actually, this was the case for the Boeing, because there the sensor just went wrong. It provided wrong data, and then the pilots couldn't prevent the accident. And the primary safety goal was to reduce the sudden loss of actuation hazard in this system. And the goal was to compare different topologies. So the baseline is a single microcontroller. Then we had to develop architectures of multiple microcontrollers with different communication architectures and with different strategies for shutdown after degraded operation and different models of hardware errors. And we executed a sensitivity analysis regarding the sensor failure rates and to other component failure rates. And creating many stochastic models by hand is very, very impractical and error prone. So we had a language, an architecture description language that is quite similar to what we have learned today in SysML. So mainly blocks and connections. And we provided language for that. And we also provided automatic transformation from the design models to the stochastic models. And this way, we could evaluate a huge number architecture models and different versions of this system, and we could evaluate which one to use. Actually, for the analysis, we used the stochastic Petri net formalism. Have you ever heard about Petri nets? Oh, you're my best friend. So Petri nets can be used to describe distributed and concurrent systems, and you can extend them with probabilities. In this case, they are the proper means to analyze stochastic systems. And what we did is that we provided a transformation that was mapping from the architecture models to the formal models. And we provided not just a mapping for the building for the blocks, but also for the associations, for the relations, and also for the software part, the sensor fusion part. So this way we could construct 22 configurations very easily. Actually, it was about actually it was about 10 hours to develop all these models. Before that, actually, it was 100 hours just to create one single analysis model. And we used 2 structure models, 3 behavior models, and various error models. And after creating these models, we just had a huge computer in Amazon in the cloud, and we ran all the analysis. It took 6 hours of CPU time to do the Markovian analysis. It was done by our own statistic analysis tool that is actually quite efficient. So it's about 1 order of magnitude more efficient than the other tools available in the market. And this way, we could just show to our partner which are those architectures and sensor fusion programs that are safe enough, and from these solutions they could choose the cheapest one that is still conforms to the safety standard. So what is very important, so even in the automotive domain, they will not use the safest solution. They will just use the one that is still enough to conform the standard. And by using our methodology, so in this domain, it's very important to find a cheap solution, because if you just sell, let's say, 5 million cars, and you can just have, let's say, 1 microcontroller less in each car, and the microcontroller costs, let's say, €1, okay, or let's say 3 reals, then you can just spare, let's say, you can save huge money, millions of dollars with this. So if you, by using this methodology, they could reach a huge saving we, compared to if they would just use, let's say, the safest solution. So this is a case study where we used architecture modeling, where we used software modeling and model transformations and analysis. And by combining all these technologies, we could save huge money for a company. So that is what I wanted to show you. If you have any questions, I'm here and I'm happy to answer them. Actually, all these tools are open source and they are available. So if you are interested in this kind of things, you can use these tools, and I'm very happy if I can help you, not only related to this case study, but also the other materials I mentioned you. So as Fatima told you, this is a 4 years long project. So I hopefully come here quite often, and it's a long collaboration. So I'm very happy if you will use these tools and apply them here. Okay, thank you very much for your attention. Sorry for making so long this day, and see you tomorrow. Tomorrow we are going to use this Yakindu tool. Actually, you can use your computer if you want, but tonight I will not sleep. I will just prepare the virtual machines for you, and you will have the exercises that you can do. Next week there will be an additional occasion in the laboratory in one morning. We haven't yet decided when you can also come ask questions, show me your solution, and the deadline to give the solution, to show us the solution, will be, I guess, Thursday. So that you can expect. So thank you very much and see you tomorrow.